In this video, we're going to look at an interesting application of using different differentiation rules. The reason why I say it's so interesting is because we're not necessarily going to deal with functions as we're used to seeing them, like a quadratic or a rational function, something like that. We're simply dealing with the names of functions, and we're going to use them to take derivatives of themselves in different contexts, defined as this h of x, to find different values of the derivative of h at different x values. So the setup of this question is that for the following exercise, we're going to assume f of x and g of x are both differentiable functions, which means that we can take the derivative of them. That's what that means. They're able to be derived, of which they have x values given in the table below. So we have x for 1, 2, 3, 4. F of 1 is 1. G of 2 is 16. D of f over d of x, what that translates to is the derivative of f with respect to x. It's just a different symbolic way of writing f prime of x. So this is the derivative of f with respect to x, similarly as this is the derivative of g with respect to x. Okay? So in that same way, f prime of 3 is 4, and g prime of 4 is 0. So we can see how this table is kind of working, depicting the different values. So we're going to use this table given to calculate the following derivatives that were given. So in this first question, h of x is defined as the function x times f of x plus 4g of x. So then we want to try to evaluate what h prime of 1 is. So the first step in this process is going to be to figure out, well, what's h prime? What's the derivative of h with respect to x? And in order to find that, we're going to use a couple different differentiation rules that we've learned in this chapter all at once. Namely, the first one is that when we add functions like this and try to take the derivative of something like this, we know that the derivative of this sum is the sum of the derivatives. So we can take the derivative of this piece and this piece individually and then add those two derivatives together to get our derivative for the whole thing. So we're fine there. Let's look at this first piece here. We have x times f of x. Since this x is a variable of our function that we're using, it's our input, this is going to be defined as a function in and of itself, this x. So what we're going to have here is we have this function f of x times another function x. So what happens when we try to take the derivative of two functions multiplied together? We have to use the product rule. Okay? And then we look at the second piece and we have 4, this constant, times a different function that we can derive. So what we're going to have here is the constant multiple rule. We can leave this 4 off to the side and not worry about it, and then just take the derivative of g of x by itself. However, that derivative would happen in a normal situation, but for our case, what that's going to involve is just adding an apostrophe. But let's look at the product rule here for this x times f of x. And since I normally call different pieces of the product or quotient rule h and g, and those are being used in this question, I'm going to use j and k instead. So we call j as x, we call k as f of x, j prime is going to be 1, and k prime is just simply going to be f prime of x. This step involves taking the derivative of whatever we define this to be. So when we take the derivative, since we don't know what the function actually is, we just say, okay, this is the derivative, this is how we symbolically note it, so we're good there. So what h prime of x will look like is we're going to use the product rule for this piece, and then the constant multiple rule for this piece. So let's worry about plugging in things for the product rule first. So how the product rule is going to look, I'm going to kind of write it down, and then we're going to plug things in to what we know. So the first bit is going to be j prime of x times k of x plus k prime of x times j of x. Right? So if we have the derivative of 1 times the original function, we just switch whichever one we're taking the derivative of and which one we're leaving as the original function when we add these two in the other part of it. And then we're going to add with the constant multiple rule. The only way that's really going to get derived is if we leave 4 by itself and then take the derivative of this. So that's going to give us 4 times g prime of x. So at this point, what we're going to do to figure out what h prime looks like, we're going to plug in our different j's and k's in these first 4 terms that we have here and see what our derivative looks like. So j prime is 1, and k of x is f of x. All right? So we have 1 times f of x, so this will become simply f of x. So then we have k prime of x, which we define to be f prime of x, times j of x, which is x. And all this is still added with a 4 g prime of x, right? We're going to keep that tagged along. So this first product here becomes f of x, and then this other product becomes x f prime of x times f prime of x, and then we have plus 4 g prime of x. So this is our derivative function in this case. So we've done part one. We found the derivative. And now the question asks us, we'll evaluate that derivative at x equals 1. Okay, so let's come over here and evaluate h prime of 1. So here we would get f of 1 plus 1 times f prime of 1 plus 4 times g prime of 1. Okay, so let's use our table to figure out what all these little f's and g's are. Okay, so f of 1 is going to be 1. So we have 1 plus 1 times f prime of 1. So we look at the derivative row, look in the 1 column, and we see 0. So 1 times 0 evaluates to 0. So we're going to have 1 on there. That's all we're really going to bring down from this first bit. Then we have 4 times g prime of 1. So we look in the g prime row, and we get at x equals 1, g prime of x evaluates to be negative 54. So then we do 4 times negative 54, and that evaluates to negative 216. So h prime of 1 is then 1 minus 216, or negative 215. This is how the process is largely going to work for the other 3 questions, but we're also going to look at them and write out the solutions of how to solve them because they all involve a different rule or different combination of rules inside of them. But this is what we're dealing with. We're going to use the function that we're originally given and use a different differentiation rule that we've learned to get our derivative and then evaluate it at the x value that we're asked to evaluate it at. So in our second question, we have a different definition of what h of x is. So here we're going to write, we have question 2. So if h of x equals f of x divided by g of x, let me go ahead and separate this off just so we know what we're dealing with. So if h of x equals f of x over g of x, then h prime of 2 equals what? Okay, so first glance at this, I wonder what rule do we need to use to derive this? So at first glance at this function, we see h of x equals a function divided by another function, and we know that when we have something like this, where 2 functions are being divided like this, we have one specific rule of differentiation that we like to really use in this case, and that is the quotient rule. So the quotient rule, in this case, I'm going to go ahead and use the names of these functions that we have here because they're already represented in the high and low form, so we can kind of keep track of them very readily in this case. But the fashion that the quotient rule will follow is low d high minus high d low all over the square of what's below. Okay, so we have our form set up. Now we just need to find out how these derivatives are written, and this is actually really the form that it needs to be in, right? Because we don't know what our functions are. We just have written them symbolically as in this is a function, this is a function. So we have this original function times the derivative of the high function minus the original high function times the derivative of the low. So all we really are going to do at this point is see how this looks in the case of h prime of not 12, but 2. So in h prime of 2, all the x's that we wrote in the first step that we had there become 2's. So we get this times g prime of 2 all over g of 2 squared. And then we go ahead and reference our table back to know what values to plug in for where. So we know g of 2 is 16, f prime of 2 is 2. Then we're going to subtract again this product, and I'm going to go ahead and bracket it off just for my own personal reasons. So we have f of 2 evaluates to be 2, and g prime of 2 is negative 24. close the bracket off, and this is all over the square of 16, because we said g of 2 is 16. So here, what this becomes is 32, 16 times 2 is 32, minus negative 48 over 16 squared. So this becomes 32 minus a negative becomes plus. So 32 plus 48 becomes 80. And then 16 squared evaluates to be 256. And we know that both of these are divisible by 16. So in order to simplify this fraction, we get 5 over 16. So this, in this case of how h of x was defined, we've evaluated h prime of 2 to be 5 over 16. So now let's look at question 3. So again, I'm going to go ahead and give us some little break in the action there. So question 3 asks us that if h of x equals 2x plus f of x times g of x, then h prime of 3 equals what? So with this definition of h of x, let's look on each part of the sum that we have here, because we're going to use the derivative of the sum as the sum of the derivatives, so we can take the derivative of this piece first and then this piece individually and add them together. So let's look at what the derivative of this is going to need to use and the derivative of this is going to need to use. So here, in the first bit, we have 2 times this function x, so we can use the constant multiple rule, or we could also use the power rule. Both of them are going to give us the same result, and I'll show you how that works just kind of really quickly. So when we use the constant multiple rule, essentially what we're doing is we're excluding the constant from our derivative process. So if we take 2 times the derivative of x, we know the derivative of x, we're going to use the power rule inside of here. So what this becomes, this derivative of x just becomes 1. So we have 2 times 1 equals 2. But if we use the power rule in the same sense, we get 2 x to the 1. We bring that power down, so we get 1 times 2. And when this x gets subtracted, its power gets subtracted like that, it becomes 0. So it also becomes 1. So this also becomes 2. So the constant multiple rule and the power rule are both equally at play, with a variable being raised to 1, but they both give you the same answer. Whichever way helps you to better visualize it, you're more than welcome to, but both of them are in play at the same time. So, with that being said, I'm going to go ahead and clear that off. We know that the first part of our derivative is just 2, because we take the derivative of 2x to give us just 2. But then, what do we need to use here to take the derivative of a product like this? Well, kind of gave it away, but it's the product rule. And in this case, I'm going to use the names f and g again, because those are the things we're taking the derivatives of whenever I write out our product rule form, how we're going to represent it. So what this looks like is, as long as we take the derivative of the first one, we have to multiply it by the original function of the second one, and then we add that to the derivative of the second one times the original function of the first one. So this is our derivative. This is how we've evaluated it, and this is what we've come to. So the question asks us, well, what's h prime of 3? So anywhere we see an x in this problem, we're going to plug in a 3. Like this, g prime of 3, f of 3. And then we're going to consult our table of values that we have to tell us what our different values are. So this 2 is going to stay because it's a constant, but then f prime of 3 is 4, g of 3 is 2, g prime of 3 is negative 6, and f of 3 is 5. So let's take out these multiplications and then add up their sums. So we have 2 plus 8 minus 30, or we get 10 minus 30, which is negative 20. So in this case of how we've defined h of x, we found our derivative, and then we evaluated h prime of 3 to be negative 20. So we have one more situation for a definition of h of x that we're given, and that's question 4. So what question 4 asks us to do, I'm going to go ahead and give us some room here. So question 4 asks us, well, if h of x is defined as 1 over x plus g of x over f of x, then h prime of 4 equals what? Okay, so the first thing we gotta do, just like the other three problems that we've done, is take the derivative. But in order to do that, let's figure out how we gotta derive each of these pieces. So this 1 over x is interesting because just like in question 2, where there were multiple ways to, or it was question 3 rather, multiple ways to look at taking the derivative of 2x, whether it was constant multiple rule or power rule, we could use two approaches to take this derivative of 1 over x. We could use the quotient rule, or we could simplify this fraction in a way and then use the power rule. Okay, and what I mean is that 1 over x is equivalent to saying x to the negative 1. If we move this denominator x into the numerator, what happens is it has the same power, it just gets a negative sign tacked onto it. And then we ask, okay, well, since that has a power, let's use the power rule to find the derivative of it. So we bring this power down, so we have negative x, and then we subtract 1. So we get negative x to the negative 2, which is also equivalent to saying negative 1 over x squared. And we would also get the same answer if we were using the quotient rule. The reason why I didn't use the quotient rule is because it's very much overkill in something like this, because you have to figure out, okay, so I have low times d high minus high times d low, all over the square root of what's below. It would work out to be the same thing. It's just a lot more of a process in and of itself to use than it is to just simplify this and get used to seeing this written as this for its derivative. So we know that the first piece of our sum for our derivative is negative 1 over x squared. We've taken care of that. And then for the second piece, we see again, well, it's going to be quotient rule again, right? Because we have a function divided by another function. So let's use the quotient rule to find the derivative of this piece, and then we'll have our derivative. So the quotient rule, say the rhyme with me if you want. It says low d high minus high d low all over the square of what's below. Like this. Okay, so we found our derivative. This is our derivative, but now the question asks us, okay, evaluate that at x equals 4. So h prime of 4 is going to become negative 1 over 4 squared plus f of 4, g prime of 4, minus g of 4, f prime of 4, all over f of 4 squared. The reason why this became 4 squared is because this was just an x, so we were plugging in 4 for x, so we get this. So let's evaluate this. This becomes negative 1 over 16. Simple enough, we're good to go there. Now we're going to consult our table that again we wrote over here. All right, I'll have it here this time so we can see it. So here, f of 4 we know evaluates to be 10. G prime of 4 is 0 minus g of 4 is 0 times f prime of 4 is 6. And then f of 4 squared is 10 squared. Okay, well, before we get too far into evaluating this fraction here, let's look what happens. 10 times 0 is 0, 0 times 6 is 0. So if we have negative 1 over 16 plus 0 minus 0, or 0 over 100, this goes away to be just 0, right? So our answer is simply negative 1 over 16. And this is our derivative of this function being evaluated at x equals 4.